Thank you, Mr. Chairman. This is the agenda. I'll cover timing and filtering, and talking about crystals and crystal oscillators in timing, and MEMS oscillator for timing, and kind of the future of timing in smartphones. And then I'll go into the SAW and Bohr filters for filtering, and then the future of timing in smartphones. There's some terms I'd like to explain a little bit. Frequency control in smartphones, I focus mostly on piezoelectric technology inside smartphones. There are some clock generators and things like that inside smartphones. I'm not going to consider that for now. For me, I think frequency control actually have two kind of the facets. One is frequency generation, which I call timing. So usually you have crystal resonators, crystal oscillators, and the base materials is quartz. And there's a frequency control part of it, which I call it filtering. And of course, there's SAW filters and Bohr filter. Bohr filter, of course, cover F-bar and SMR. And the base material is lithium tantalate, lithium niobate, or aluminum nitride thin films. So for timing inside a smartphone, basically the timing is the opening of this door, is it at the right location? So there's an RF spectrum, okay? You want to have a very good timing to make sure that's synthesized at the right location for RF transmissions. So that's timing. Filtering, of course, is once you have the correct opening, then you want to make sure that the width of the opening is correct also. So that's controlled by the filters. So I think timing and filtering are both very important inside smartphones. And we used to call crystals Bohr, but of course today Bohr is being taken over by F-bar and SM now, so we just call it crystals. And you can see that there are three columns here, and they cover different technologies. First is crystal. Crystal usually sub-megahertz to about 200 megahertz. And SAW-based devices usually 50 megahertz to about 3.5 gigahertz. And the Bohr devices usually 1.5 to about 5 gigahertz. And you can see that the black ones here are those what we call frequency generations. And then the red ones are frequency controls, usually filters. And one with the red box, okay, those are the devices you usually find in smartphones nowadays. So you can see that you can see tuning fork and crystals and some SAW filters and some F-bar and SMR filters also inside. And you can also see TCXO in some of the cell phones also. So these are pretty much the crystal or SAW components inside smartphones nowadays. And there are some, of course, you can see there's some F-bar or Bohr-based kind of devices they make into oscillators also. I put down here some of them. Most of them are not productized yet, but you can see that the VCFO here, which is the F-bar-based voltage control oscillators, is now available from Avago on the lower left here. So again, these are those in the boxes are those components you can find in smartphone nowadays. Crystal. A lot of you are very familiar with crystal for many years. Okay, crystal using quartz. It's very high Q, but it's a low coupling. But we care much about Q. And in the past, when there was IF filtering inside cell phones, okay, and usually you have using quartz to do IF SAW filters also. But of course, today's most of the smartphones nowadays don't have IF filtering. Everything is direct conversion now. So there's only RF SAW filters or F-bar filters inside. And crystal is a very long history, and you can see that the metal can type or the small size ceramic kind of the ceramic packaged devices nowadays. Okay, and it's basically a very important resonant element for an oscillator. And these are some of the kilohertz and megahertz crystals and TCXO inside smartphone nowadays. You can see that this one is a kilohertz crystals. So you can see this one is very small. This is a 2 by 1.2. And actually, the crystal inside is very small. It's because it's packaged inside a ceramic package. And you can see that this is a tuning fork. This is not the traditional tuning fork anymore. You can see the ankle is being bent around, okay, to reduce the size. Okay, it's still a tuning fork, but the shape is different from what you saw before. And usually about 100 ppm over the temperature range of operation. And down here is a megahertz crystal. Megahertz crystal, you can see that this one is a 2 by 1.6. And you can see that it's also very small. And the crystal is inside, you can see it right here. And usually a megahertz crystal, you're talking about less than 50 ppm. On the right side, you can see the T6. Those are the T6 still being used by some of the cell phones nowadays. And usually it's about 2.5 ppm. And the size is, you can see that this one is about 2.1 by 1.7. Okay. This is a table listing the small size crystals, Kilos crystal, megas crystals, and TCXO available in the market now. You can see that those ones right before the sampling, those are in mass production now. You can see there's a 32 kilos crystals. Mass production is 2 by 1.2. People are sampling 1.6 by 1. This is very small. And the megas crystal, you can see that is now down to 1.6 by 1.2 being shipped in volume. And the 1.2 by 1 is being sampled. Now, people are talking about 1.0 by 0.8. I don't know how they're going to do it. It's so small. And the TCXO, you can see that I showed you the 2 by 1.6 one just now. And you can see that now it's actually the sample is 1.6 by 1.2. And people are talking about 1.2 by 1.0. Now, this is an oscillator, so it has a crystal and an IC inside. The problem with crystal today, I think the crystal technology is that because you still have to manufacture single layer methods. So you do it one piece at a time. And usually use SIM seal or solid seal using HCC leadless chip carrier. And chip scale packaging, wafer level chip scale packaging, wafer level packaging for crystals or crystal oscillators is either difficult or impossible. And of course, there's also 100% in situ time trimming difficulty also. All the crystals and all the megas crystal, Kilos crystals or TCXO oscillators, they have to be tuned 100% before encapsulations. And the other thing is that as crystal goes small, there's a lot of problems also. The ESR, the impedance is getting very high. And this is a table listed some of the suppliers. And so you can see that from the table. Obviously, when it gets smaller, the impedance got higher. It's more and more difficult to drive in oscillations. And of course, there are other issues also. The drive level sensitivity also. You cannot also drive the crystal. The crystal is so small, so there's not as much volume of the crystal to absorb energy. So you cannot drive very hard also. So you can see that as crystals get smaller in this table, you can see that the drive level allowance is getting smaller also. Of course, there's another big issue is that about the impedance. So you can see that there's a paper last year. You can see that the people actually looking at using photonics kind of crystal to improve or to reduce the leakage of the energy, so to maintain good impedance. Okay, this is a very interesting idea. I think if you look at SAW and FBAR also later on, you can see that a lot of efforts are being put into reducing leakage. For FBAR, of course, the anchor loss. And for SAW, of course, is the transverse mode, the diffractions, all those things. How to minimize the leakage loss is a big deal now for today SAW devices and FBAR devices also. Of course, a few years ago, we are beginning to see MEMS oscillator come in also, okay? I think the MEMS oscillator companies started out a little bit difficult in the beginning, but I think that we are seeing some really good advancement in the MEMS oscillator. You can see that there are 32 kilos MEMS oscillator available out there now. They're trying to compete with 32 kilos crystal. So customer can buy a 32 kilos MEMS oscillator and just drop it in. In general, it's much easier to use oscillator than crystal. Crystal, you have the low cap, okay, to tune the crystals. And if you use an oscillator, it's much easier to use. But of course, using oscillators is a little bit more expensive. But I think with the MEMS oscillator technology moving ahead, I think there's a chance that they can actually compete head-on with crystals also. So I like to show this here, that you can see that I showed this table just now, but you can see that actually side time will get over these two MEMS oscillator 30 kilos directly compete with the small size quartz crystal. The size are almost the same, okay. Of course, for MEMS oscillator, there's one problem, okay, you have to drive it. So you can see that actually, you can see the MEMS oscillator here. There's two extra pads there because you need to drive it. Okay, it's an oscillator. For the crystal, it's just a passive device. TCXO has been used in the smartphone for many years. The first, I think the first generations of iPhone, okay, use two TCXOs inside, one for the transceivers and one for the GPS. But at least for the transceiver, back in 2007, 2008, you can see that NXP, okay, their transceivers, okay, began to use just crystal, just a piece of crystals, and instead of a TCXO. Back then, of course, the TCXO was expensive. Crystal was much less expensive, so there was a lot of incentive, okay, to use crystals. And of course, to do that, you need to have a thermistor, okay, close to the crystals also. So if you look at this, this is a crystal, and next to it, there's a thermistor, okay, to sense the temperature. But it's okay, it still uses just the crystals. But of course, nowadays, some of the newer generation of smartphone, they don't have any TCXO inside now. They still use a crystal and use a single crystal to drive both the transceivers and the GPS. And of course, now they put the thermistors next to the inside the package alongside the crystal. You can see that this is what we call thermistor inside crystal. You can see the crystal on top and then the thermistor underneath it. So it sends directly the temperature of the crystal and do the adjustment. So I mentioned that this 2008, this is the second generation of one of the biggest smartphone companies in the world. Back in 2008, they used a total of 6 crystal components. 2 TCXO, as I mentioned, one for GPS and one for transceivers, and then 4 other crystals for different applications, for Bluetooth, Wi-Fi, for the CPU, and for the baseband. So a total of 4 crystals and oscillators. But in 2014, in their 6th generations of iPhones, this company stopped using TCXO and actually use just 4 crystals. But they also added one function, which is NFC, the near field communication. People usually thought that if you have new function in there, you use new crystals. But somehow they managed to use one crystal to drive for the CPUs and the NFC. So the problem we are saying now is that smartphones seems to be using less and less oscillators and crystals. The SAW community has gone for a lot. I list here that I call it the first wave, the second wave of application of SAW. I mean, in the past, any Japanese companies you mentioned, like Sony, Sharp, Hitachi, Toshiba, Mitsubishi, Toco, Toyota, every one of them were doing SAW devices for mobile applications. But many of them left the field because the price dropped so much. And you don't find too many discrete SAW filter suppliers nowadays. But of course, today things change now because of the LTE. Smartphones can have easily like 20, 30 bands inside, and every band has to have 1 filters. And so filters seems to be back now, okay? I'll explain a bit more. So my thinking of the third wave for SAW is kind of the new wave is filter inside modules for smartphones. Skyworks landed 2 modules. And one is the pad module. The pad module basically is a PAs with switches and duplexers inside. And then we also announced diversity module, which is LNAs plus switches and filters now. So basically nowadays smartphone now we are moving toward basically between the antenna and the transceivers, all those PA switches, LNAs are going to be modularized. Okay, the module will cover low band, mid band, and high band. Low band usually under 1 gigahertz. Covering some of the LTE bands under 1 gigahertz. And between 1 and 2.2 gigahertz, we call it mid band. And from 2.2 to 2.6 gigahertz, we call it high band. And of course, there's the band 42, 43, which is mostly used in China now. And that's 3.5 gigahertz. I call it very high band. So all these modules will cover different bands, okay? So we can see that I mentioned that every band you have the 1 filters, but the PAs advanced a lot. 1 PAs can cover several bands now, basically. Okay? So we can see that for the modules now, the cost of the module become heavily reliant on the filters now. The filters cost inside the modules become the highest cost inside modules. So for all these modules company now, they have the PAs, they have the switches, but they must have their own filters, internal filter supplies now. This is exactly what Skyworks is at this situation. We must have our own filter supply. And this is also for some of the other modules companies like Avago, like Quovo, like Murata also. Of course, early this year, TDK and Qualcomm announced the joint venture. This is exactly what they're going to do. They're going to do modules. They will do all these PAs, RNA switches, and filters inside modules. So this is a chart showing some of the bands I mentioned. I mentioned that easily there are 20, 30 bands, okay, for some of the newest smartphones, okay. And some of the bands are easily more suitable for FBAR and SMR. Some of them are for SAW, what we call standard SAW, and TC SAW. TC SAW basically temperature compensated SAW. And I'll explain a little bit about this. SAW, as you know, is a long history, okay. SAW, the frequency is very simple. SAW velocity divided by the lambda. The higher the frequency, the smaller the lambda, is more difficult to produce. Okay, basically you can see that for 2.5 gigahertz SAW filters using a 4,000 meter per second. So you can talk about the line width is about 0.415. It's around there, nominal. Okay. And then once you have a SAW, and then a one-port SAW resonator is the building element for a filters. So you build the SAW resonators, and then you cascade them and become a SAW filter. You can see that on the top right there. And Bohr actually covered two technology. One is called F-bar, one is called SMR. And basically, it's this copied from the crystal industries. Basically, it's that you have a piece of piezoelectric materials, top and bottom electrodes, and you excite in motion. So this basically copied from a crystal, but of course, this is much higher frequency because the film can be very thin. Okay, and you can see that for 2.2 megahertz F-bar devices. Okay, you're talking about the film thickness about 2.5 micron, and so the higher the frequency, the thinner the film thickness. Okay, and so a little bit. So you can see that I already mentioned the SAW can easily go up to about 2.5 gigahertz, but beyond that it's a little bit difficult because the line width is getting thinner. The same thing for F-bar. F-bar is easy to, they go up to 3.5 easily, okay? But when they go to lower frequency, they have problems also because the film will be very thick. So if you build a low frequency, the F-bar resonators, okay, you have to deposit very thick film. Plus also when you go to thicker film, then you also have to extend the XY dimension, so the device becomes bigger also, okay? There's another technology, SMR, which is, they call it a surface mount resonator. It's a little bit like F-bar, except that they don't have an air cavity there, but they just use the black reflectors, okay? Kind of layers of different materials, okay, to reflect wave back and create a resonant, okay? So I kind of have two, okay? One's F-bar, the SMR. For SAW-based and Bohr-based filters, I think I kind of listed the strength and weaknesses. And Bohr, of course, can go to higher frequency. But SAW usually a bit higher coupling. Coupling is important because higher the coupling, you can sustain a little bit higher bandwidth also. And then Bohr has a better power durability. Usually for SAW devices up to a watt, and Bohr-based devices easily to 3 to 5 watt. Higher Q, F-bar has higher Q. And they have lower TCF, but I mentioned that the SAW has advanced a lot also. Now we have the SAW device have what we call TCXO also. Okay, I have the high power durability already. And Bohr devices really a bit more expensive because there are a lot more mask levels. And then Bohr devices also can only take care of single end, and SAW devices can do balance or single end. This is a chart of some of the SAW materials, substrate for different applications. The SAW industry spent a lot of time on this for many years. But today, for handset, for smartphone applications, we only use two kind of materials. One is the lithium tantalate, YX36 lithium tantalate. The other is the YX128. Those are high coupling materials. And those are pretty much all the SAW company manufacturing SAW filters for handset now use these two materials now. I mentioned about TCXO. Basically, TCXO is that there are two ways of doing it. One is that you put the substrate on top of a silicon or sapphire. So you use the silicon and sapphire to limit the movement of the substrate. Okay, so by doing that, okay, you basically reduce the linear expansion coefficients. Okay, the other way is that you put silicon dioxide or some dielectric coating on top of the substrate, and then by doing that, you change the wave type and you change the wave velocities. And doing temperature compensation. You can see that the top methods, okay, can reduce, because lithium tantalate is about 45 ppm per degree C. By limiting its movement, okay, you get down to about 15 to 25 ppm degree C. If you put silicon dioxide on lithium niobate, okay, you can go from 80 ppm to about 25 ppm. In fact, you can actually get it to 0 TC. I can put it down to 0 here. So both technologies have different strengths and weaknesses. Usually, if you use lithium tantalate on silicon or sapphire, you don't have to do redesign. Basically, the same filters. Okay, but if you do on silicon dioxide and lithium niobate, you have to completely redesign in the IDTs. Okay, because everything's changed, velocity changed, the coupling changed, the reflectivity changes. And then for the lithium tantalate on silicon sapphire, okay, there's a 4-inch and 6-inch possible now. Lithium niobate is still only 4-inch. And the Q, of course, the lithium tantalate one, there's no change of the Q, basically. But if you do silicon dioxide on lithium niobate, actually you can improve the Q. In the past, the experience is that if you put something on top of the SAW devices, you de-Q the SAW device, but it's not necessarily true. If the right thickness of the silicon dioxide to lambda ratio, you can actually improve the Q. Of course, 0 ppm is possible for lithium niobate. The other thing is also lithium niobate, you can, by changing the silicon dioxide thickness, we can change the coupling. For lithium tantalate, you cannot increase the coupling. This is just some designed structures for SAW devices. I'll just skip this one here. Basically, this is just to show you that currently we do a lot of duplexer. Duplexer, we have two filters inside. One is for receiving, one is for transmission, sharing the same antenna. The one on the left side is that for SAW device, we can use the ladder type on the left, and then you will what we call the double mode design on the right. Ladder type is basically acoustically coupled, electrically coupled all these SAW resonators. DMS type, basically, you acoustically couple the SAW resonators. Okay, they are different technology. So usually DMS can be smaller. Okay, you can see that comparing the left on the right, you can see that we can process both devices on one substrate, but the one on the right, because the ladder usually is a little bit bigger. Okay. And this is the size of the duplexers and filters that nowadays. You can see that most of the we manufacture SAW filters now basically wafer level chip scale package. The substrate become part of the package now. And you can see that for a duplexer, you can get it down to about 1209 size. And for single filters, we're talking about 0605. These are single filters. Of course, the thickness is going down also. SAW and bore, they are different technologies. For myself, of course, I work on SAW. And I think that SAW has a lot more parameters to play with, even though it has a deficiency in terms of the, it doesn't go to a higher frequency. But of course, there's different kinds of SAW waves. SAW is a very complicated technology. It has different kinds of SAW waves. Currently, we are only using the rayleigh wave for the lithium niobate, and for the lithium tantalate, we're using leakage surface wave. But there are different types of SAW waves. And that we can exploit in the future, okay, to increase the coupling, to have better temperature coefficients, or to increase the velocity. Okay. Of course, people are looking at also Lamb mode also. Basically, this is a very good explanation. You can see the F bar is like a piezoelectric thin film sandwiched between two electrodes, and SAW device basically is a very thick substrate, and you excite it on top. But if you using a SAW device, but thin it become, make it very thin, okay, then you actually excite the plate mode. This is exactly basic of the Lamb mode nowadays. Lamb mode is being investigated mostly for timing application, but it's the same thing. For timing application, you look at resonators, but you build filters or resonators. So if you have good Lamb mode resonators, ideally you can build good Lamb mode filters also. And the other thing is this is like a 3.5 gigahertz SAW filter. This is from Murata back in 2 years ago. They're looking at band 43, which is 3.5 gigahertz, okay, very high frequency for SAW. And you can see that at that time, Murata looking at different technology. They're looking at aluminum nitride on diamond thin film, of course, and zinc oxide on sapphire, YZ, lithium niobate, ZX. So there's still a lot of opportunity to go up to that kind of frequency for SAW devices, okay. F bar doesn't seem to have as many parameters to play with. Okay, you can see that the one on the left is from a while ago, back in 2005. The one on the right side is 2014 from the Korean company. You can see that the structures of F-bar filters or resonators is pretty much the same. The shape changed a little bit, okay, from polygon, okay, to oval shapes, okay, just to avoid patterns, okay. But the basic structure is pretty much the same. Okay, it's top and bottom electrodes on aluminum nitride. Okay, so for F-bar, I think in the future, I think they will focus more on the TC, temperature compensation, how to do temperature compensation on the F-bar, reduce leakage, very important, okay. As long as if you mount the devices, you will always see leakage, okay. How do you reduce that? And also piezoelectric thin film, aluminum nitride is not polycrystal. People are talking about doing the single crystal aluminum nitride. Does it buy you a better coupling? Buy you better Qs also? So those are the things people are looking at also. Of course, wave type also is a possibility. I mean, if you look at crystal, they use different wave type. They use thickness shear, they use extensional mode, and different type for different applications. So I think for F-bar people, I think they are also looking into different wave types also. Prospect of timing and filtering in smartphone. Basically, smartphones continue to increase the volume. Okay, just skip this. Okay, this is just for timing. This is my observations. Okay, may not be right. Oscillators are no longer needed, but it's not necessarily true. Okay, because there are still a lot of cell phone, not necessarily smartphone. They still use TCXO because it's easy to use. And TCXO price came down so much that it's slightly a little bit more expensive than crystal nowadays. So it's, if you have a choice, you should use TCXO actually. Okay. Crystal miniaturization is near its end. Okay, it's very difficult to get crystals of small size because you have to package a crystal. Okay. Small size is more expensive, and small size has high resistance. And then you can see that transceivers and GPS sharing crystals. New functions in smartphones seem to be supported by existing crystals, so people are not adding new crystal inside. And many suppliers continue to drive down the ASP. Integration into modules are not common. Okay. Not like the filters, SAW filters. You can see they integrate into modules now. Of course, MEM oscillators may pose threat also. On the filtering side, you can see that this is a number of filters needed inside the phones. Okay, you can see this is for a smartphone company from the first generation to 6th generation. Okay, you can see that the number of filters inside continue to increase. Okay, these are either SAW filters or F-bar filters. Okay, this is the final slide. My opinion is that there are no substituting technology in the next 5 to 10 years in terms of performance, size, and cost to compete with SAW and F-bar or ball devices. And the carrier aggregation, the downlink, and you basically in the future, I mean, in the forthcoming few years, you can see that a lot of downlink is not only using one RF band, there are several RF bands together. So you use several RF bands to downlink information simultaneously, okay? That we call carrier aggregation. And other spectrum sharing advances will make it even more difficult for other technology to compete with SAW and BAW for now, yeah. Okay, thank you.